Okay, so last couple of days, okay, we've been dealing with acceleration, velocity versus time graphs. Okay, what we got to remember is that that acceleration is a change in velocity over time, or change in speed over time. Okay, so that's the formula that we'll be using, okay, to solve all of these here on this quiz. All right, so for our first question, we got the large rock rolling down a hill towards the road, and the driver first sees the rock, it's traveling at 7.5 meters per second. When the rock reaches the road, it's moving faster at 13.5 meters per second. If the rock was accelerating at 4.4 meters per second squared, how long, that would be time, did the driver have to come to a stop? All right, so their first mark for their givens, the acceleration was given to us as 4.4 meters per second squared, okay? And since all of these are since a direction is not given, we have to assume they were all in the same direction. Okay. In fact, this essentially is becoming a scalar question where you're looking at speeds as opposed to velocities because vectors were never given here. Okay. Give them another mark for selecting the correct formula. A equals VF minus VI over T. In order to solve for T, I first multiply T over to this side and then divide both sides by A. All right, and then give them a mark for their correct manipulation, a mark for plugging in the numbers correctly. 13.5 was our final speed, minus 7.5 our initial speed, divided by our acceleration, 4.4. Okay, and their final mark, fifth and final mark, is that he had 1.36 seconds to react. Oh, yes, sorry, I didn't do significant figures. Yes, you are absolutely right. No, sorry guys, I did this quiz before we started doing that. You are 100% right on that. 1.4 seconds, two significant figures. Okay? Good eye. 5 marks, yeah. Any other questions on that one? The fifth one's for the answer. Okay? 1 for givens, 1 for the formula, 1 for manipulating, 1 for plugging in numbers, 1 for the answer. Okay, second question. Wile E. Coyote drops an anvil. Hopefully you all know who Wile E. Coyote is. I know that's like a generation gap thing. He's the guy that tries to get the Roadrunner and all the Bugs Bunny and Tweety show cartoons. I know you guys probably didn't watch that because I'm older than dirt and you're not. Okay? Now, he's always trying some sort of stupid trick to catch the Roadrunner, rocket-powered roller skates, and dropping anvils off cliffs, okay, things like that. Everything's made by Acme, okay? Anyway. Okay, so the anvil falls for 6.5 seconds. That's one of our givens, okay? The other givens are things that it doesn't outright tell us, but that we have to know, okay? If we're dropping something, then it wasn't moving at the beginning of the question. Anytime something is dropped or released or falls, okay, then its initial velocity is 0 meters per second, okay? If it isn't 0, then it would say it's thrown at this velocity or projected at this velocity or something like that, okay? All things on Earth, regardless of their mass, fall at 9.81 meters per second squared. Okay, that is the rate of gravitational acceleration on Earth. Okay, that's another number that anytime you see a falling object, you know that number applies. Okay, or even if you have an object that's thrown vertically into the air, that number is going to apply as well, 9.81. Okay, so give them a mark for their givens, a mark for choosing the correct formula, A equals VF minus VI over T. This time, we are looking for VF. So the first thing we move is T by multiplying both sides by it, and then we add VI, which is easy because it's 0, okay? And that leaves us with VF. All right, so mark for the correct manipulation, A times T plus VI, or VI plus A times T, doesn't matter what order, okay? And then a number for plugging, or a mark for plugging in the numbers correctly, 9.81 times 6.5 seconds plus no velocity, gives us a final answer for our fifth and final mark of 64 meters per second, because there's only 2 significant figures in that one. Okay, guys, quiet, please. Yeah. Meters per second squared down, yes. Yes, absolutely. If you had negative 64, it just, in this case, it asks how fast, which is speed, a scalar quantity. If they put a vector on it, that's fine. If they have down or negative, that's okay. Okay? All right, questions there? All right, give him a mark out of 10. Let him see it, and then put him on Hannah's desk here, and I'll collect them. So over the last couple of days, we've been doing all this stuff to do with velocity versus time graphs, okay? And we've been dealing also with A equals VF minus VI over T. So I just want to quickly review a couple things here about velocity versus time graphs, okay? And some of this may apply to your need for speed lab, the one we did yesterday. Okay, so as I go through this, you may want to pay attention to a couple of big juicy hints that'll be dropped in regards to maybe some of the analysis, okay, for that particular lab. Okay, if I've got a velocity versus time graph, okay, so velocity on the y-axis and time on the x-axis, okay, and it goes like this. Okay, so let's say this is section A, section B, section C, section D, and section E. Okay, what is it doing during part C? It's accelerating negatively. It is going backwards for part of section C, but not all of section C. Okay, that's how we know it's got to be accelerating. Whoop. It's got to be accelerating because obviously it's got a slope that is negative for this part, and slope from a velocity versus time graph is acceleration. Okay, and just a quick review here. How do we know that? Well, if I find the slope of this line, okay, what I'm really doing is finding the change in velocity, VF minus VI, and dividing it by the change in time. Right? Rise over run. That's essentially what I'm doing for that section of the graph. Okay. Now, at what point does this object actually start moving backwards? Right here. This is where it actually starts to move backwards. It's accelerating backwards through all of section C. Okay? But for this part, its velocity is still positive because it's still above the x-axis. So, okay, I mean, obviously these are all positive values up here. These are all negative values down here. It's still moving, but it's going slower and slower and slower, and then for an instant, it's essentially stopped, and then begins to actually move backwards, right? So this would be if I think I used this example yesterday, attached to a rubber band, okay, like, or a bungee cord or something, and I'm moving this way, but as I stretch the rubber band, okay, it's actually making me slow down and accelerate backwards to the point where I can't stretch the rubber band anymore, so I actually start to go that way. Not just accelerate that way, but actually move that way. Okay, everybody all right with that? Okay, this could also be a graph of something thrown upwards into the air. Okay, it would be moving upward, but slower and slower and slower until it reached its maximum height, and now it actually begins to fall downwards, even though the whole time it's accelerating downwards. Okay? If this was a graph of an accelerating object, what would the slope, or sorry, of an object thrown up into the air, what would the slope of this graph, of this part of the graph be? Okay, if I throw something up in the air, what's pulling on it? Okay, so what should the slope of that line be then? What number? 9.81 meters per second squared. Okay, everybody all right with that? Does that sort of make sense? That's something that I'll often put as a multiple choice question, okay, seeing if you can interpret what's going on in this graph. Like I would say, you know, what's going on in part A? Well, the object is accelerating positively. Okay, what's going on in part B? The object is traveling at a constant velocity. Going on in part C, accelerating negatively. Okay, and then I would ask, at what time, so I would have the time intervals on here, okay, at what time does the object begin to move backwards? Okay, that's what we just said. Right here, it's where the x is. That's where its velocity goes from being positive to being negative. All right, so those are the kind of interpretation questions you could possibly get. Okay, so let's say I've got a velocity versus time graph that looks like this. Okay, so I've got my velocity here, time on this axis, and I've got this line that goes like this. And the question asks me to calculate how far has the object gone. Okay, how do we usually calculate displacement from a velocity versus time graph? Anybody remember? Right, we find the shapes, right? Because by finding the shapes, we're essentially doing this. We're taking the average velocity and multiplying it by the time. That's giving us d. How many shapes are there here? two. There's two shapes here. There's a triangle and a rectangle, because this object didn't start according to the line anyway. The points might say something different, but the line says this thing at time 0 was already moving at some velocity, okay? Which would be my, what do we call this thing here? Well, actually, the origin is down here. This is the y-intercept, right? This is b, okay? So now, if I've got all of that, I should be able to calculate, okay? If I know the time here, maybe I've calculated that. That could be an x value, okay? I've got a triangle and a rectangle that I need to calculate. So basically, I'm saying, here's how far I would have traveled had I not accelerated. I would have started at this speed and stayed at this speed the whole time. I would have gone this far. But I did accelerate, so I actually went further than that. I have to add on how much did I change by. So that's the height of the triangle multiplied by the base of the triangle, because again, okay, the height of the triangle divided by 2 gives me the average velocity. Multiply that by the time, I've got the area of this triangle. Okay, for this, it's just the rectangle. All right, ringing a bell? Okay. Again, those are things you're going to be asked to do on a unit exam to do with graph. Okay. What happens to the distance it takes you to stop if you go faster and faster? It increases, okay? Hopefully that much is obvious, even if you haven't taken driver's ed. That's going to be on your driving test, okay, at some point. The thing that they don't tell you is that it doesn't increase linearly. The distance required to stop is dependent on your mass and how much energy your car has. Okay, we're going to talk about work and energy later on in the week, okay? But the more energy your car has, the farther it's going to take to stop, exponentially. Okay? That means if I go 10 meters per second, it might take me, let's say it takes me 20 meters to stop. If I go 20 meters per second, it's going to take me 4 times that much, 80 meters to stop. Okay? It's an exponential relationship, and again, I'll show you why, okay, when we get there, right? But it also has something to do with how acceleration is related to distance. This isn't a formula that you'll use in Science 10, but it is a formula you'll use in Physics 20, okay? Where we start bringing in that area that's underneath the line, okay? That's where we start bringing this in. Okay, we find the change in velocity and we divide it by twice the distance. That gives us the acceleration. Okay, all right. So just something for argument's sake there. Okay, the other day I gave you a worksheet that had a bunch of acceleration problems on it. We didn't get much time to work on that the other day. Okay, so I want you to take that out right now. Are there any that we need to go over? I'm assuming most people probably got maybe like the first 8 or 9 maybe done. Okay. Anybody done more than the first 10 on that sheet? Okay. Okay, so you guys made good progress on that. All right. So first question on that sheet, guys, was this one. We did this one in class about the race car. Okay. And I think we did this one in class too, with the guy dropping the water bomb. Okay, I don't think we did many others after that, but are there any that have been giving you trouble that we'd like to go over right now? All right, hey, 4, yep. Is that this one, the proton? Okay, so we've got a proton that's accelerated in a linear accelerator. This is kind of like the Large Hadron Collider thing they have going. It's a particle accelerator, and they smash things in. They try and make really big stuff. Well, big in terms of atoms, big, okay, out of it. So we've got this thing, and it's being accelerated. The acceleration is 800 meters per second squared, which you can do with incredibly small charged particles because they're incredibly small. Okay, you could never accelerate something at this rate if it was large. Okay, but they do this acceleration. How long does it take the proton to get from rest to 2.5 times 10 to the 8 meters per second? Okay, so I've got VF here given to me. It's this, okay? 2.5 times 10 to the 8 meters per second. Is that fast? It is. It's very fast. It's relativistic. That means within a reasonable percentage of the speed of light, which is that fast. Okay? We have, of course, never been able to make anything go that fast. Okay? Einstein's law of relativity kind of explains a little bit of the energy required to make something go that fast and how it becomes basically infinite, okay, as you approach the speed of light. So we're also told in this question that VI is at rest, or 0 meters per second. Okay? And we know the acceleration is 800 meters per second squared. Okay? Those are the values that we're told. We're looking for the time in seconds. So we start out with A equals VF minus VI over T, and we manipulate for T. So we multiply both sides by T, and we divide both sides by A. So we'll have 2.5 times 10 to the 8, which you punch into your calculator the same way you did Avogadro's number. You got to put it in brackets, use the E button, okay? Minus 0 over 800. Okay, so when I punch that in, okay, it's going to have to look like this. So brackets 2.5, whoop, not 0.5, 2.5, okay, E8, okay, and since it's minus 0, I'm not even going to bother writing that in there, divided by 800. Right, gives me 312,500 seconds. Of course, that's not correct for significant figures. Okay, did I change those on yours? I think I did. Yeah, I did. Yeah, or I changed them on the key on my website. I gave you 2 sheets. Okay. Anyway, I'm pretty sure it's right on the website now. If it's not right on the sheet you have, that should actually be 3.1. Sorry, how many? Yeah, 3.1 times 10 to the 5 seconds to the proper number of significant figures. Okay, because this number here only has 2 significant figures. Okay, everybody all right with that? Okay. Now, how did they do this? Anyone know? How does that Large Hadron Collider make things accelerate? It's a supergiant electromagnet. Okay. What happens is because protons have a positive charge, you get these big magnetic fields which repel particles, and they can make protons and electrons move and accelerate greatly because they run away from magnetic fields and electric fields if their charges are right, and so they accelerate these things along in this tube. Okay, and this tube is really, really long, kind of circles around itself, okay, to make a really long distance for them to accelerate, and then there's a smasher at the end where all the particles run into each other. Okay, and then they try and build big particles out of that. It's pretty funky, actually. Okay. All right, any other ones giving us trouble? All right, let's keep working on that for a little bit at least, okay, and then if we're doing well on that, we'll move on to work energy theorem today. Okay, listen up here, guys. Okay, so we had a request here for number 16. So we got a particle, so that's basically anything, anything could be a particle, moving with a velocity of 112 meters per second at time 0. So is this VI or VF? VI, because it's happening when the question starts at time 0. Okay, so we know that VI is 112 meters per second. The particle has no acceleration until time 3 seconds. So in other words, it's going to travel at this speed for 3 seconds. All right, so time equals 3.0 seconds. And that means this has got more than one part to it. Okay, they're describing a part where it first travels at a constant speed and then does something else. Okay, after which it has an acceleration of -4 meters per second. So in part 2, okay, its acceleration is going to be -4.0 meters per second squared. Okay, and it's asking us, what's the velocity at time 16 seconds? Okay, how long does this part take? The first 3 seconds we did this, traveled at a constant speed. Then we accelerated for the next 13 seconds. That's the trick on this one, okay? Is that part 2 is 13 seconds long. The whole trip is 16, okay? Part 1 is 3, part 2 is 13. All right, and how fast am I going when I start part 2? This fast, right? Because I travel at a constant velocity for 3 seconds. So this is not like a test your math ability question. I know you guys can do that part of it. This is a reading comprehension question. Okay? And unfortunately, a lot of physics comes down to that, is being able to read the question and interpret what's going on. Okay? I think I was telling you guys about last year's physics diploma exam where they had like 2 pages of reading to answer 2 questions. Okay? Which we thought was brutal, but that's what they do sometimes. So we want to make sure that you guys get some experience in reading long, convoluted, verbose questions. Okay? So 112 meters per second is the starting velocity here. All right. So what's the velocity at time 16 seconds? Well, do I need any of this? None of this is important. There's no acceleration in part 1. Okay? It's just there to confuse you. I don't need it at all. It's just there to tell you it only accelerates for 13 of the 16 seconds. That's it. Okay? So now it comes down to looking for VF. All right, so I got A equals VF minus VI divided by T. I want to get VF by itself. So if I want to move something, I do the opposite. Multiply that side by T. Multiply this side by T. Then move A over. Okay? Sorry, don't move A over. I want A to stay over there. I'm looking for VF. So what do I do with VI if I'm subtracting it right now? Want to move something, I do the opposite. All right, so I'm going to add it to this side over here. All right, now VI is gone, and I'm solving for VF. Okay, and again, intuitively, that should make sense. Here's how fast I was going at the beginning. Here's the change in velocity. That should give me how fast I'm going at the end. All right, so we got 112 as our initial, plus 13 seconds times negative 4.0. So am I going to get a smaller number for VF here? At least it's going to be more negative, right? It's slowing down according to the question. Okay, so 112 okay, plus 13 times negative 4. All right, so my final velocity should be 60 meters per second. Okay, and that's got to be positive because they gave me positive in the question. All right, questions there? Cool. Mm-hmm. Because for the first 3 seconds it didn't accelerate. The velocity didn't change. Right? It only accelerated for 13. Yeah. Okay. Other ones? That's okay. Ask. All right, keep going then, guys. Okay, so we got a request here for number 21. Okay, and number 21 is another example of a multi-part question. Okay, so what ends up happening here, guys, is you do a calculation for part 1, and you use one of the answers from part 1 as the start for part 2. Okay, so we got to read the question carefully and make sure that we're getting all the information where it needs to go. So it says here first off that it starts from rest. Okay, so I know at least that much. VI is 0 meters per second for what I'm going to assume is part 1. Okay, and it accelerates at 2.01 meters per second squared, which is positive, so it's going faster, for 7 seconds. Okay, at the end of this time, the boat continues for an additional 6 seconds. Okay, so part 2 is going to be 6 seconds long. Okay, with an acceleration of 0.518, which is also positive, meters per second squared. Okay, following this, all right, that's another part then. Here's part 3. Okay, the boat accelerates at negative 1.49, so now it's slowing down, meters per second squared, for 8 seconds. Okay, what's the final velocity of the boat after all of this, which is 21 seconds. Okay, the 21 seconds is not a piece of information we're using in any of the 3 parts. It's how long the whole trip is. Okay, so I don't really need it. Okay, if I'm going to do any calculating with part 2 or part 3, I mean, if I want to know what VF for part 3 is, I need to know what VI for part 3 is. Agreed? I don't have that. Okay. However, the initial velocity for part 3 is how fast it's going at the end of part 2, because it transitions from part 2 to part 3. The problem is I also don't know what that is, okay? Because I don't know what the initial velocity for part 2 is. But the initial velocity for part 2, similarly, is the final velocity from part 1. All right, so I've got to find the final velocity here by going VI plus T times A. Okay, so manipulating our formula for VF. So we'll have 0 plus 2.01 times 7, right? Which should give us 14.14, is that right? 14.07. 14.07. Okay, 14.07 meters per second, and that's positive. All right, I bring that over here. That's how fast it was going at the end of part 1, so it's how fast it was going at the beginning of part 2. Now I've got one more piece of information. So it's the same calculation. I got to find VF. Okay, so that's going to be VI plus T times A. Just some of those numbers are different now. Okay, so we've got 14.07 plus 6 seconds times 0.518. Okay, our acceleration. So that's A, that's T, that's VI. All right, so 14.07 plus 6 times 0.518. So 17.178 is my final velocity for this part. Okay, everybody all right with that? Okay, now I bring that over here. That's going to be VI for part 3. Okay, now I can solve for VF. Again, same calculation we've been doing all the way along. Okay, is there a problem? Okay, so we've got 17.178 here then. Okay, plus the time, which is 8 seconds, times our acceleration, negative 1.49. So okay, so we have a final velocity, okay, in part 3 of positive 5 point, what do we have for significant figures there? It's 3, so 5.26 meters per second. So yeah, it's a lot of calculating, okay? And no, I would never give you one like that on a test because it's the same calculation 3 times, okay? I don't need to test whether you can do it consistently, okay? Just whether you can show it to me once, all right? Okay, any other ones?